messing up my fall break. So, but I'll just do that and just turn it, and then I won't care when you turn it in. We'll just do it that way. But yeah, you got to worry about that. You know, the grading part's always the worst part. So it's just what we delayed that. That's good.
Sir? Are you going to be mostly on the whiteboard?
It's gonna actually this time it's gonna be here.
I'll try to.
Although it is, I'm gonna do a tiny bit on the whiteboard. You're right. I know this class is I've learned it.
Strongly agree.
Yay, I've learned it. Yeah.
Well, they don't take a house. No, but at least
I just it's English work. Good. Okay, good.
At college? Yeah. Of course I am. I started in college because that was when eyesight was bad.
Yeah.
So it was there.
Yeah, I got it at work.
No, she's coming. She said. I know. That's nice.
I can bring it in if you want.
I'm actually using it when I have Tuesday.
Yeah, that's a nice program. I came out of college, so actually made it pretty good.
And they didn't agree. It used to be.
Oh, yeah.
It's like the graphs that they put out were, they were good graphs, but they were really poor looking.
No, they're not anymore. They're nice.
So we used to take them if we wanted to see it, take it to grow and set up.
Yeah, I don't think you have that problem now. He's probably on the way with his kid. It's not going right. If we are, probably in Albuquerque.
We should have some fun.
Yeah. Yeah, exactly. It should be, I did that. I've done what I have down in Australia. They sent me down there to try and translate for that. Yeah, we were on the other, 12 hours away, you know, on the other side of the world. She's part of production, but I don't know, I'm not really sure how it is. I know she was involved in, pushing things too, that she didn't event together and all that. Lots of people. Yeah, I told her you're probably on the way.
It's a good play.
Yeah. Are you back? Yeah, yeah.
It could be.
No, we were
So this should be fun, I think. And I like this chapter. And I like where we're heading. We'll see if y'all get agree. So what we're doing today is the complete and incomplete blocks and the Latin square. So what we're at, you know, we're at the point where we've got data and something messes us up. Some background variables are causing us to want to put things into blocks so that we can still make our conclusion that is the treatment doing something. So we don't care about the blocks. The blocks are background variables, and you'll see, you know, if you've read the chapter, if you've read the, you know, when we talk about it, you'll clearly see what the difference is. We don't care that the blocks cause variation. We know they do, because there's some background variable, different subjects or something. So we want to take that variation out so that we can still make a decision on our treatments or not. And then the Latin square is a particular set of, so when you do this, I guess what I'll say is you'll have a 2 by 2, right? You'll have the blocks, which are your different subjects or the background variables, and you'll have your treatment. So that's like a 2 by 2 matrix. The Latin square is a way to take 3 factors and put it into that format. So it's sort of like squishing a 3D thing into a 2D array. So it's a special case, and so it fits well within the chapter. So what I'll do to bring you to where you can do this is we'll do the math prelims, which I've now scanned in, and so I can do less on the board. And then I'll go to a PowerPoint that's got an example in it. And the PowerPoint's one I got from another, you know, just searching on the internet and found one. It's got a really interesting example that I think I like it because it's an example. It clears up. I mean, the book does too, does a nice job, but it shows exactly what we're doing. And it makes sense to you. It's about testing and studying format, so I think it's a very easy to understand example. And then, oh yeah, I've got an Excel with this too. So I've got there the example described in a PowerPoint that I swapped from somebody, and then an Excel spreadsheet with it. And so then that'll do our blocks, and then since it's a bifurcated chapter, we'll talk about Latin square too. And to do it, I found a paper online by a person named Dura. That's why I call it the Dura paper. And so we'll go through it, and it's got an Excel too. And it does a nice job, I think, of illustrating what a Latin square is, and it does the mathematics for your Latin square. Because that doesn't quite fit into the Excel format. I mean, I've used Excel, but it doesn't. You can't just pick a Latin square out of the data analysis and do it. So it's got the math, and I'll show you that. So I've got an example, another example of it too, showing you how to use it. That's what these are. And so I've got that math, and then at the end I've got a little paper. We won't go over it, but I've got it. It's another paper about Latin square. And once you see what Latin square is, you'll understand what it's trying to do. It shows you how to construct one. And so part of what I was trying to do with this lecture too is, you know, get you a feel for something like more like a PhD class, because you can see how we've still got the math and stuff, but you know, bringing in other resources, bringing in papers. You know, so it's a little bit more researchy type of discussion, I guess, if you will, but still got the practical pieces with the Excels. And also, this is where part of our tools fail us. The Excel, you'll notice there's this, incomplete block. So there's a little piece of the chapter where they tell you what happens if you got some data missing. And it makes sense. I think the example they're giving is that somebody's testing cars. You've got a bunch of drivers. So the drivers are your background variables that create the block. Each driver's different, and they can't all drive all the cars. You know, again, we've got these problems. And so one idea would be, well, let every driver drive every car, and that's discussed in the first chapter. But then the other idea is, well, suppose you can't even do that. So you've got holes in your data. Well, remember way early on we said that's one of the problems with Excel. The Excel doesn't do well with no data. You know, it does. You can't just select a table with big holes in it and say, do me an ANOVA. It's going to be hard on you. So our tool fails us in the incomplete block diagram. We can't use Excel, and so it's in the book, and I'll point it out and we'll talk about it in a minute. But if you have that situation, now, so I guess, so what do I say? Then don't do that. You know, or if you do have that situation, you're going to have to go to another tool, like Minitab or something like that. And I should spend a little time investigating that, but I haven't yet. But I will for us. So, So I can make at least some comments on, hey, here's what's mine. The book talks about it, so we know it could, something like Minitab could do it, but our Excel can't, but that's okay, because hopefully, like you got some control over your data, or control over your analysis, and you can, at least in the near term, you can, avoid that, and if you can't, okay, well, learn Minitab. So anyway, so that's where we're going. So remember, the central thing is, this chapter we've moved away from just the happy world of everything's homogeneous, and we've got some problem with background that's requiring us to block our data sets so that we can account for the variation due to the background. We're not going to get rid of it because it's there, but we can at least account for it and take it out of our variation and still answer our question, does the treatment matter or not? Because otherwise, if we've got all these background variables in there, which we know cause variation, then that's just going to mask our treatment variation. We won't be able to answer the question. So we're trying to set it up where we can do that. So let's look at the math a little bit and see what's involved, what goes into the ANOVA, and then we'll go into the PowerPoint that'll give us a good example, and then we'll look at the special case. So that's where we're headed. So let's see what we've got. So our goal then is we're going to look at one treatment that's varying, at least initially, but we're going to randomize things within the blocks, and the blocks exist because of a background variable, something that changes that we can't control. So we have to accept the fact that we've got these blocks, and they're going to cause variation, and so we're going to randomize our experiments, our treatments within this block, and then account for that variation. So let's see how that works, and why? Because remember, we're trying to minimize the amount of variation that we can't understand, right? If I've got, like our little chart, our little picture said, well, in fact, I shouldn't draw it. It's right up in here. Yeah, there. I don't need to draw it on the board. Yeah. So remember our chart, we've got some variation in our data. And this is the chart that grows through the book. And chapter 2, we just had these pieces. We had the treatment that caused our data to vary, the thing we were caring about, like the insulation thickness or something. And then we had random error that always exists. So this is what we're trying, wanting to find the treatment variation. Random error is always present. You're never going to get rid of that. And so now we've added, we've got this background variable that's a result of the different experimental conditions that's also causing this variation. So as long as we can explain this and account for it and calculate it, then we can say, okay, look, we've got this total variation like we're always looking at, SS total or SS error, the sum of the squares error, and we can say, oh, well, gee, we've got this total error, and it's made up of these three parts, and if we can explain away this or measure it or calculate it because of our ANOVA and our mathematics, then we can get rid of that, and then we can compare this to this and ask our same F statistic question again. Is the treatment matter, or does the treatment just look like random error? And remember, that's what we're doing with our F. If the ratio of this to this is 1, that says, oh yeah, it's just random. But we can't ask that question if we can't separate this out, because otherwise it's just going to tend to into these, and it'll just confuse the issue. So we've got to be able to organize our data and do an analysis where we can suck that variation out too. So we're going to use the same inferential method that we did in chapter 2. We're going to use an ANOVA. We're going to get our F statistic. We're going to get our little P, whichever way you look at it. And remember, all we're doing is, you can ask the question either way. We've got this F distribution, and we're either asking, we're going to calculate our F as our treatment, the ratio of the treatment to the error, and then we're going to look up some F critical and some percentage. We pick that. And if our F falls out here, say our F calculated falls out here, then we say, oh, that's very unlikely. Remember, that's what we're always asking. And why? And it's unlikely because, well, gee, say we were looking at the 5%, the F for 5% area out here is here, and we're way out here. Now, we don't have to look at it that way. We don't have to compare our F to F critical, we can also just go out here and calculate this, right? And that's the P. And if we calculate the P, we can compare P to 1% or 5%, or just compare it to itself. So remember, we're just looking at, so it just depends on which way you like to look at it. Do you like to compare one number to another limit? Do you like to compare probability to the probability limit? Either way, the question is the same, the answer is the same. It's just how you interpret it. Are you comparing where your F falls to a line, or are you comparing this total probability out here to some value? It's either way. And this F critical, you're going to have to pick some arbitrary limit. You know, you could just calculate this P and then come up with it and say, does that look like it's small? but you know you're going to ask the same question. Does that look like it's small compared to 1%, compared to 5%? So we're still going to use the same test, and it's an inferential technique because, you know, we're trying to make an inference. We're not just measuring statistics and calculating something. We're trying to infer something about the greater population from a sample or a test. So let's see. So mathematically, what are we doing? So in general, oh no, you know, it's terrible, but we're back to the same problem, and I probably should write it up here too, just to emphasize it. So we've got some treatments, you know, thickness of insulation, different cars, if we're looking at gas mileage, how you applied the learning technique in the example later on study. And then we've got blocks. So we're going to arrange the treatments in the columns and the blocks in the rows in our data table. And the blocks are your background variables. Like in the book, they're looking for gas mileage, so they've got the car going this way, car 1, 2, 3, 4, 5. And down here, they got the driver. Driver A, I'll still use number C, D, and A. And so then they're going to measure the gas mileage for the driver going over the same course and the same speed, those kind of things. And so mathematically, we've got a model of our data point. And we've got any general data point, the ijth data point is the average, the overall grand average, plus, remember before we had the treatment variation and we had random error. So now we've added this block variation. You know, notice how the block, you know, varies with the row, right? And the treatment varies with the column, and the random error is you know, independent of each of the samples. So what am I saying? So I'm laying it out. Put here, you've got your data in here, so let's pick some random data point here. Y, I, J. So, you know, in this case, I would equal 2, J would equal 3, and it equals the mu, which remember, mu is just the entire average, right? Average over everything, plus this block, beta I, okay, plus the treatment here. Yeah, so this one guy here in the ij position has a value that depends on the overall mean, depends on the error due to the block, the error due to the treatment, and a random error. Okay, so now can we separate that out? Can we mathematically deal with figuring out this one, and for all of them together, sum them all up, sum of the squares, add them up, you know, look at the ratio of this to this over the whole table and decide, oh, this matters, or oh, this doesn't matter. So what do we got? The ijth piece of data, the overall mean, the block effect, the treatment effect, random error. So these notes you got if you need them to. Okay, so let's see. So we assume that the treatment effect is the same for all the blocks, okay? In other words, there's not any sort of interacting things that if I apply treatment number 3 in this block, and this block, it's going to affect things the same way. There's not some sort of interaction. So when I go to treatment 4, there's not an interaction between the blocks or something like that. And just like before, our hypothesis that we're testing is that the treatment doesn't matter. And then we're going to run this ANOVA, and if we find out that our mean square error for the treatment, and remember the mean square error was where you summed all these up, squared them, so you took care of pluses and minus, and then the mean square you divided by the total number, so you normalize things. And so, if we find out that matters, then then if that's bigger, if that falls out here, you're going to conclude, gee, that's unlikely that this isn't happening. It's our null hypothesis is false, and we've got something else. There is a treatment difference. And remember, we had that issue as well. Just because F falls way out here, or P is little, we don't know which treatment it was, right? There's 5 treatments here, 5 treatments, 5 different cars, 4 different drivers, but those are the blocks. I should put that word too. These are the blocks here, the treatments here, if you're going to use words. And other statistics books use the same words. And so, if we do conclude that F falls out here and that the treatments matter, we don't know which one. Again, so we're stuck with doing some further analysis to identify which one. Maybe all of them are, contributing. Maybe just this one. And we have to do that Tuckey or Sheffy type approach where you compare each one. But it may be obvious too. You probably can eliminate some, or you can do that. Remember that Sheffy approach had that where you put some combinations of them together and maybe eliminated a whole bunch of them all together. But we do know if we come up with F falling back here, then the treatment didn't matter. That's maybe more the useful thing. Oh, okay, it doesn't have any effect. None of these cars mattered, or none of the insulation thicknesses mattered, or something like that. Alrighty, so let's see. Yeah, and the key point here is what we're trying to do. Remember, we don't care if we can statistically identify this, right? That's not our goal. Our goal is not to say the blocks matter. We know it matters. That's a background variable. It's goofed us up. It'll come out. The ANOVA will spit that out. You will see that the blocks matter. Sometimes they don't. But in our example, they will. That's not our goal. Our goal is to be able to account for this so that we can find out if this matters. Because that's our central question. Did the thing we do, the insulation thickness, the car, whatever, does it have an effect? So we're not doing this so we can identify that background variables matter. Hopefully background variables do matter. That's why we classified them and understood them as a background variable. So that's not our objective. Let's see. So what we're going to do mathematically, and I won't beat you to death on this. It's the same math that we did in chapter 2. Okay, what all they do, all of these books do, they take this total variation and they rearrange it. What are they doing? Oh, they're doing things like let's see. They're saying, hey, for a given variable, first they subtracted mu, stuck it on the other side. Then they're saying your variation from the block is the block average minus the overall average. Remember that I and the dot you summed over the whole block? Or the treatment, remember it was the sum over all the treatments. So the block average would be this way, the treatment average would be that way. And so compared to the overall mean, and then the random error is just the random EIJ. And so all they're going to do now is play around with each of these. You see they do things like, let's see, here they've subtracted mu, here they've grouped things together, calculated this a different way. Look, they're calculating this based on the original equation. Regrouping things, let's see, playing with just algebra there, let's see. Yeah, let's see. So they've just basically rearranged. So that's for your block, that's for your treatment, that's for your random error. And and again, the math, if you're interested, you can read it, study it. I don't think it's critical that you could derive this thing because it all comes down to the ANOVA tool anyway, and that's what It's just laying the prelims of what's in the ANOVA tool. But you guys, do you want me to go through the steps on it carefully or not? And would you rather take it and study it? You know, these are, yeah, the notes are online, and it's the same math that's in the book. And they're not doing anything, like I said, they're not doing anything amazing here. They're just rearranging. And then let's see. And then they're given here the definitions of what everybody is. Let's see. Some over the treatments, some over the blocks, some over all, and normalizing each time. Yeah. And they're changing notation. Yeah, let's see. Yeah, see, they're saying, hey, the row average is this, the column average is that, the overall average is that. Yeah, that's the number of treatments, that's the number of blocks, so that'd be the total number of data points. So this case N would equal 4, in this case K would equal 5, so N times K equals 20. Yeah, you have 20 total data points. So you can see what they're doing. This is the overall grand mean, the mu. That's the column mean, yeah, over the block. That's the row mean. Yeah, some over the treatments. Yeah, some over the treatments in each block. Some over the blocks in each treatment. Some over everything. So you can see kind of what they've done. Alrighty, let's see. So they substitute their new notation in, the double dot, the single dot sums. Let's see. Then they square both sides and add it all up, because remember, that's what we were trying to do. That's how we were getting these square errors. And our goal was to look at all these errors, and the reason we were squaring them is, again, to get the pluses and the minus to be okay. So we're trying to look at how everything varies from each of these means. You remember our ANOVA lecture last time where you had the overall variation, the variation from the block, the variation from the treatment. They sum it, they square it, and they break it down. So your sum of your square total error was the sum of the square with the block, sum of the square with the treatment, and sum of the square with the random. So this is our new piece that showed up now, as opposed to what was in chapter 2, because we've got these blocks now. Remember, chapter 2, you didn't have blocks, you just had data, right? You had the different treatments, like we had the insulation thicknesses, then we just had data points. We didn't divide it up into blocks. So now we've got this variation. Let's see. So let's see. So that's our fundamental ANOVA equation. So we're not going to use that single factor ANOVA, right? This is single factor. We just had one treatment. Now we've got two factors. So when we go under our data analysis tab, we're going to have two factors. The two factor ANOVA. You saw that in there. There's two factors without replication and with replication. This is going to be without, because we're only going to have one data point in each segment. We're not going to have multiple. We'll do that later. You can compare it to what equation 2 looked like. And remember on page 21, let's see, equation 2 should not have the block in there. So equation 2.8, yeah. So equation 2.8 had that equals that plus that. Because yeah, we don't have any blocks. So now let's see. So now what do we got? Yeah, we've got degrees of freedom, and we always discuss that because of the mu. They're always 1 minus the number of blocks, 1 minus the number of treatments, or the total 1 minus the total number of variables. So then you could find out the degrees of freedom of the error if you wanted to. We know the total, we know the blocks, we know the treatment. So we didn't know what the degrees of freedom in the error was. And there it is. Okay. All right. So now, can we use ANOVA? Let's see. I should probably leave the. Yeah. Okay. I can do Latin square here too. Make it be continuous. So now we're gonna. So we've got a different ANOVA, and it's probably easier to wait to see it till I get to the example, but in the book on page 52, your results in your ANOVA now, instead of just having the treatments and the error, we now have blocks, treatments, and errors. So the two-factor ANOVA has another row one to account for the blogs. It's got all this summary data in it, and so we'll look at it. We'll look at it when we get to here, I'm sorry, not there, to the PowerPoint. So, but it'll be clear, I think, then. So we've got a ANOVA that we can use with this two-factor if our data is arranged carefully. And then what we'll wind up moving to as a second piece is this Latin square. And I'll cover it again when I pull up the paper. But what the Latin square does is you've got these blocks and you've got a treatment, and maybe you've got another one. You've got two things, two treatments, if you will, basically. So what it does is it allows you to efficiently analyze them under a certain condition, and that is here. Yeah, your rows and columns are your number of treatments 1 and treatments 2, and your number of blocks are the same. So that's an unusual set of conditions. But if you're controlling things, like one of the papers I read said this occurs often in animal experiments, like cosmetics or something, when you want to limit the number of animal subjects you're using. So you can control the fact that I have only M blocks, and I can make it be the same. And so if you have this special case, you can arrange things in a particular way that makes this work still with the two-way ANOVA, with a similar two-way ANOVA, not quite the one out of the Excel, and I'll show you how. And so we can include a third dimension, if you will. Here you can see we've got 2 dimensions, blocks and treatment 1. We can include a third, treatment 2, and also use the same technique. And so we'll have, rows, columns, treatments, and error. And so I'll show you how that works. It's only a special case, and we'll do that with the Dura paper. So now that we've got this mathematical background that hasn't really, it's probably more confused the issue that made it clear, but you know where we're headed. We're looking to get rid of that so we can still examine that compared to that. Let's look at a real application with somebody's PowerPoint and see if it clears it up. Alrighty, so we'll see. We'll see if we like this person's approach. Let's see. Yeah. So they're laying the same preliminary ideas, right? When they say reduce variability, they mean let's reduce or account for this effect so that we're now only looking at what we want. Yeah, is there more than one factor? Yeah, there's some in our experiment here. In this car idea in the book, car matters in terms of gas mileage, right? Of course, big car, little car, but so does the driver. And we may do the best we can and explain to the drivers, everybody drives the same. It still doesn't matter. We still believe that the drivers matter. So let's take care of these. Yeah, so let's look at a multi-factor design. That's what this is. Multi-factors, more than one. Yeah, this is a block design. Right? Two-factor without replication is the tool we're going to wind up using. So here's an example where this might happen. Our question is, again, I'd like to lay all this out on the table. I've just explained to you in ViewGraphs. But their postulation in this thing is, does the way you study for a test matter, whether you study for a lecture or out of a book or on a videotape or the internet? And they've got some scores of people. And so the question is, well, does it matter? And just looking at them, you say, well, I don't know. But you also could postulate that there's some background data messing this up. What background data could mess it up? Well, maybe this group of folks was smarter than this group. Maybe these are all the A students because they all like going to the lecture, and these are all the ones that want to sit at home at night in their pajamas or something. And so maybe it's not fair. Can we come up with, is there a background variable messing this data up that'll hide us, and we'll just conclude, there is no difference. And so is there a way we can get rid of this background data? Well, no, if we didn't collect any information, no. This is all we got, well, no. But perhaps we might have more information about each of these students, because we're a high school or something. Perhaps we know what they scored on the SAT. So could we postulate that the SAT sort of tells us, your SAT score sort of tells you whether you're smart or not. Let's divide them up. Let's put some blocks in there, smart students, moderately smart, lower, and let's put those blocks. And then we can, if we can block the students amongst the smart and the not so smart and all, then we can maybe answer, did the treatment matter? Oh, okay, well, that makes perfectly good sense to me, so let's see. So match pairs, okay, we could do that. Yeah, so we're trying to decide if and this is an explanation of what I just said, if the learning mode affects the score on the final exam. Yeah, I mean, by chance, we could have had all the people that were good in math in the lecture, right? Or all the people who were good in math on the internet, and would hide things. So let's see. We got multiple populations. Experiment consists of a series of B blocks, in this case 4 in this example board, and K levels of the treatment. So in our book they use N, in this book they're using, in this presentation they're using B. That's good. Actually, it makes it easier, maybe I would have used T for treatments, T and B. Got to think about these things. So these are the basic ANOVA assumptions here. Okay, so let's see. Each teaching format, one person scored on the math person on the SAT. Okay, so here's our blocks, right? So we're going to say, we had all those students. Now let's look at their SAT scores. Anybody who got over 700, then in this category, here's our 1, 2, 3, 4, 5 blocks that we're going to divide those students up into, try to remove the effect of smartness. All right, so now one of the things this Excel does, and I probably shouldn't go through it so slowly, they actually do all the math by hand. So they calculate all the SST, the SSE, everything by hand, which is good, I think, if you want to look at it. Maybe I shouldn't click through. Let's see. Treatments, blocks, okay. So now they've done. Okay, so here. So they've taken that random set of data now, and now they've partitioned it like we've said. So again, here was your treatments, right? Whether you did lecture, a text, videotape, or internet. And then here's our blocks, right? The smart, the not next smart, next level, this, yeah. So now when you arrange it that way, you say, okay, I can see the trending of your math capabilities here showing up. But yeah, can you see? Well, it's hard to tell. Yeah, I did. It looks like text may be worse here. This guy worse, that guy worse. You can start seeing. You better see already. You can see. You just laid out this way how it may be some trends. Okay, so here's the treatment means that way. Man, this helps. This is good. And here's the block means on this way. So now you kind of understand too what's showing up in the in the math when they're doing the sum across the columns, sum across the rows, and then the grand mean will show up. Yep, that's just average this way or average that way. It'll work either way. Okay, so now we're going to do sums of the squares, treatments for K minus 1, blocks B minus 1. Here was that equation we had. 2 total, right? Each data point minus the grand mean. Treatment. The treatment mean minus the grand mean for each of the treatments. The block mean minus the grand mean. It's a little bit better maybe to see it their way. It's a little clearer.
All right. So
the error, yeah.
start talking about
That minus that, because that comes from our direct equation, right? It comes from our
problem here is that
SST total is
each one of you,
block,
and I'm trying to clarify that.
SS treatment plus SS error. We just solve for that. Yeah.
Each one of you have different pictures.
Let's see. So now this is where
It's very well known for all of us that
they're going to lay it out for us in a table nicely. Yeah, that's good. calculate each one, and remember the mean is just divide that into that. Okay. Yeah, okay, yep. And they're saying this came from those. So here, yeah, so the mean square, just divide each of the sum of the squares by the degrees of freedom. Let's see. Okay, so now they're going to calculate the F, treatment divided by error, and then they're comparing it, of course, to 5%. Why, again, because 5% is common, right? So we're going to have to calculate this F critical at 5% based on the numerator degrees of freedom and the denominator degrees of freedom, because that's how the F statistic works. And again, that's the background of the statistics that where you go to Harvard and become a statistician and get your PhD. And can we conclude this block's different? By the way, actually, you're right. We're going to get an F for the blocks too, right? I mean, it's going to, and we could ask, maybe the SAT score didn't matter. Maybe we goofed up on our background variable. Maybe that wasn't important. So we'll see. Well, that'll show up too. It comes out of the ANOVA, right? And calculations. So we'll click through this quickly, but maybe we can look at them and see, right? I should have the data. Too bad the data's not up here in the corner. Remember the sum of the square total. This has got the grand mean, and it's going to take every data point, all of them, right? Take the difference between every data point and the grand mean, square it, sum it up. Treatment, it's got each of the treatment means compared to the grand mean, and the blocks got each of the block means compared to the grand mean. You could probably, in fact, you could look at it, right? There were 5 blocks, so you can see there's 5 terms here. The 5 blocks, remember the greater than 700, 600, 700. And there were only 4 treatments. There was the lecture, the text, the internet, and the videotape. So here's 1, 2, 3, 4. And there's the grand mean showing up everywhere. Yeah. So these are the means along the each of the blocks. So that was the ones on the road, right? And these were the means coming down the column. I'm sorry, these were the means coming down the columns. Yeah. Now let's calculate some square error from these. There. And we don't have to do this. In the nice Excel does all this stuff for us. But you can do it by hand if you wanted to, right? In fact, if you see it by hand, it may help you understand, what Excel is doing. So let's see. Did the treatments matter? So remember our null hypothesis is that all the treatment means are the same, and the alternative is, well, one of them's not. Maybe 2 of them, 3 of them, 4 of them. So at least one. Yeah. Okay. So let's see. Alpha equal 0.5. If our F is bigger than the F 0.05 and 3 and 12. So where did that come from? That table, right? Remember or Excel, the F distribution and inverse functions. So now let's see our mean square of the treatment. That was the SSTR divided by the degrees of freedom of the treatment. Mean square of the error, that was our SSE divided by the degrees of freedom in the error. Okay, let's make an F. 0.2. Okay. So it's not. So in this case, our F calculated fell right here. Really darn close. Is food here yet? Or? So that's why our F calculated fell. Kind of right on the edge. So it's saying, yeah, treatment didn't seem to really matter. It was close, wasn't it? But that's at 5%. At 1%, it'll be even worse. 1%, all right, it's going to move this F critical way out here. Even worse. Let's see. Did the blocks matter? That might be kind of. Cannot conclude there's a difference in the treatment. Okay. Did the blocks matter? All righty. Same H0, really. That's the difference, right? We had 5 blocks. Same number of errors. There's the block mean, the error mean. Whoa. Way out. So the blocks did matter, right? So kind of backwards, almost a backwards conclusion on this little thing. We thought that lecture, text, internet, videotape might have mattered. But really all that mattered was how smart the student was. And so when that fell right out real clearly, you know, hey, the F critical or the F calculated for the treatments was not even 5%. But yet for the blocks, it's hugely way out here. I mean, that P is going to be tiny, right? That probably is, you know, 10 to the minus fifth or something. So yeah, the blocks matter. Well, you know, and then, you know, you might say, well, duh. You know, I think that generally the smarter people in math are going to do better on the test. But perhaps this wasn't so clear. You know, maybe it wasn't such an obvious thing. And it made a good, yeah, there was a different blocks. It made a good example. So and here's how you would do this in Excel. In fact, I'll go through their things, and then I did it too for you. So here it's laid out in Excel exactly like it was on the video or on the PowerPoints that we did by hand. The blogs, the treatments, the data. Okay, let's see. I think he does a nice job. Yeah, you know, the two-factor with replication under the data analysis. This is actually pretty nice, I thought. He picks the whole range, or she, I don't remember who did this. Picks the whole range. So if you pick the whole range and click labels, it's going to label everything with these labels. If you just pick the data and don't click labels, it'll still do it. It'll just number them. And I show both ways in mine. Just output range. Remember, you can either output to a new worksheet, a new workbook, or you can pick a spot right here where it'll start laying your ANOVA if you want. I like to lay it on the same page sometimes to look at it. And so there's the ANOVA. And so you're going to see the same results, right? So remember, this is always the summary stuff that where it adds up the number of data points and gives you a mean and all that stuff and the variance and all that. Nice. And you see these means are the same means that were on his screen, right? These were the means across the row. These are the means down the columns. There's a variance. This is the number of columns, a number of rows, number of columns. Here were those SS numbers you calculated. So you can see ANOVA and Excel is doing nothing more than those calculations. Somebody's just done it for you and got a nice output. Here's your degrees of freedom. Here's your that divided by that divided by that. We can do that in our head, right? Then here's the calculated F. Oh, what's that? Remember, the F was just that over that. Let's see, that over that, that over that. Yeah. And then the P. Okay, 10 to the minus third on that P. I couldn't do it in my head well. So and there's the critical F's. So you can see the results. You can see the conclusion. That compared to that, oh my goodness, certainly the rows, i.e. the blocks, mattered. That compared to that, no, it didn't. Yeah, it was 6%. So, okay, 5% was out here. Where we fell was 6%. I think you should, start. Oh man, makes pretty good sense. It's pretty easy. And you didn't have to know all that math, right? We didn't have to do all the sum of the squares and divide by n. No. All we had to do was put it in that nice table, select it, and hit run. Out it came, and understand what it means. And it's nice it's nice to see the math and understand what's going on. But also, you understand it's not that complex, right? We're just taking a bunch of differences and squaring them, adding them up, dividing by some numbers. It's really not. It looks complex, and your statement is statistically nice and complex, especially to most people. But it's not bad. Yeah, there was the blocks. I already said that. There were the treatments. Yeah. The p-value for the treatments. Yep. P-value. Yeah. Can't conclude that teaching format mattered. P-value for blocks. Low. So you can conclude that the SAT mattered. And remember the thought about low. If P is low, then what your statement is saying is that's the probability, less than 1%, 1/10 of a percent, that you would just get this F value by randomness. I mean, there is a probability, right? 0.1% of the time, if we ran this test with a bunch of just regular people, that randomly you would get a giant F. Okay, but it's that unlikely, So therefore, you could probably conclude that this data shows that student mattered and treatment didn't. Blocks. Okay. We've reduce variability, we're using our without replication tool. Assumptions are that, let's see, some squares, mean squares is what we say, F-tests for the treatments and the blocks, yep, okay. And in Excel, so let's see. So do I have it in Excel for you? Yeah, let's see. I'll put it here, let's see.
Okay,
There, this one.
all right. Okay, group number one.
Okay, so I did the same thing. I laid it out for you, and I told you where to go. ANOVA two-factor without replication. Again, why is it without replication? Because we've only got one score here, right? We had a bunch of scores in that block. It would be with replication. I selected the whole thing, checked the labels box, and put C19 into the output box. So again, just your thing to see. Yep. And that's the same, you can see the same results they get. So you don't have to just rely on their PowerPoint, you got the Excel and you can use it. Yeah, just change it over. So now, if you had a different setup, right, you know, this can grow this way or this way, right? If you have more things or less or whatever, you can use the two-factor ANOVA thing. So is it seeming to make some sense? And the whole thing that motivated us was because we had these backgrounds that we couldn't control. We couldn't control which students took the test. They were already in the class, they were already in the video or the internet. We couldn't control that we had to have 4 drivers. It wouldn't, wouldn't it be nice if driver A could have driven every car all the time? I wish we could have done that. Sorry. But wouldn't it be nice if the same student could take the lecture and the text and the internet and the videotape and retake the final test? But you know what I'm saying there? That's ridiculous. Because once they took the test once, they certainly do better on it the next time. And once they watch the lecture, I'm sure they do. They do better than them reading the text. Then by the time they got to the end, they'd be doing great. I hope to goodness they're making 100. And so you completely screw up the experiment. So that doesn't even make any sense. And so you can see how this is useful. And you can see now what tool we've got now. Now we've got a tool where we've got different treatments and something that's messing us up. Time, person, student, season, temperature, something that's causing us to block the data into background blocks. Now, so now we can. Now, do we have one more?